This video will cover bond price volatility and duration. We'll discuss selected characteristics of bond price volatility. We'll compute and discuss duration as a measure of bond price sensitivity to changes in interest rates. And then we'll discuss selected characteristics of duration. So let's take a look at selected bond price volatility characteristics. And by the way, what we mean by bond price sensitivity is how bond prices change with respect to interest rate changes. That's what we're looking at. How do bond prices change with respect to interest rate changes? The first characteristic is that bond prices move inversely to yields. We know that. We've been talking about that. And so that's nothing new. The second one is that price changes are non-symmetric. That we didn't really cover. I'll show it to you graphically. Number 1 and number 2 I'll show you graphically and give you a little more insight into it in a minute. Let's continue down the list. Third characteristic is that for a given yield change, price changes are larger for longer maturity bonds. In other words, long-term bonds are more risky than short-term bonds when interest rates change. The fourth item is that bond price changes in percent increases as maturity increases, but at a declining rate. That basically means, look, if you have a 5-year bond and then you have a 10-year bond, the percentage change in the 10-year bond, which is double the maturity of a 5-year bond, won't be twice as large. It'll level off, and I'll show you that graphically. And the fifth item is that high coupon bonds show smaller percentage change than low coupon bonds. I'm not going to show you that with a graph. Characteristic number 5 is all about duration. So I'm going to show you, using duration, how high coupon bonds show a smaller percentage change than low coupon bonds. And we'll look at that in detail. So now let's look at the first two graphically. The first two characteristics. We have price here, we have yield to maturity on this axis. And the relationship between bond prices and yield to maturity looks something like this. It's a convex curve. It's not a straight line. And we see two things here. Not only is it negatively sloped, but there's an asymmetric response. So if you had let's say you had this little width of a change in yield, you would have, we come up, let's take a look at it carefully here. We would have a fairly big change in price because of that. Now, if we took the same width, let's say it's about there, and we looked at the change in price, I'm not even going to draw it because it's too hard. You can see that there's hardly any price change associated with this particular situation. So what you see is an inverse relationship. You see an asymmetric response, and when interest rates are high, bond price changes don't happen as much as when interest rates are low. We are in a low interest rate environment today. You know, interest rates are near zero, so you're going to get lots of change in bond prices for a small change in yield to maturity. Now, how do you estimate this? Well, it's pretty easy. You come up with, just plug in an N in your calculator, put in a face value of 1,000, put in a payment of, say, $25, and then you could either plug in a yield to maturity, and I/Y, right, and plug in various yields to maturity, and out will pop out a present value, or the price of the bond, the value of the bond. Or you can plug in prices and do it reverse. Plug in prices and come up with the yield to maturity, and then graph it. And graph it carefully so you get that curvature in there. So now let's look at the other two relationships. We can cover them in one shot here. So item 3 basically said for a given yield change, price changes are large for longer maturity bonds. And then the fourth one basically said this relationship flattens out. So graphically, what that looks like is this. If you have maturity and then you have price, you're going to have a relationship that looks something like that. So it says for given changes, yield changes, price changes are larger for longer maturity bonds. So if you have a long maturity bond in this direction, we got this upward sloping yield curve. So this would be change in price. Okay, so make sure you have a delta there. Change in price is larger with higher maturities, but the relationship flattens out. It's not a linear straight line relationship. It levels off. So how do we show that? Well, let's fall back on the old zeros that we used to use. Remember zero coupon bonds, probably the easiest way to look at this. And so here we have a scenario where we have a 1-year bond and a 10-year bond. So that's what we're changing. We're changing maturities here. And we have a 1% interest rate and a 3% interest rate. When I mean interest rate, yield to maturity here. And so what we're going to do is we're going to have a change in yield to maturity of 200 basis points. So let's look at a zero that matures for 1,000. And if yield to maturity is 1%, that zero is worth $990.10. And if you have a zero that matures in 10 years and the yield maturity is 1%, your 1,000, it's calculated as 1,000 divided by 1.01 to the 10th power, and that gives us 905.29. So two different zeros at a yield to maturity of 1%. Now let's look at the same zeros at 3% yield to maturity. Okay, so what you see here now is, look at this. So here's a bond with a 10-year maturity, 10 times this maturity here. And so what we have is a price change. So the change in price here was minus 1.94%. So you take 970.87 minus 90.10 divided by 990.10, and you'll get this minus 1.94%. And then here you're going to get a change of 17.8%. And so, wow, what do you see here now? What you see is that there's a significant difference in the price change here. I should put a negative sign here. And that not only do you see a significantly larger change for the 10 years, the longer maturity, which is basically what we're saying. It's like for a given yield change, it's 200 basis points. The price changes are larger for longer maturity bonds. There we have it. It's much larger. But also notice it's not tenfold. It hasn't increased 10 times. It kind of flattened out a bit, because if this was multiplied by 10, it would be 19.4%. And here it's only 17.8%. That basically shows these two relationships. Now you could calculate price changes too, not only on a percentage, but measure it on a dollar basis also to show the same thing. And you can see that with your eye, that it's a substantially larger change in dollars. Now let's move on to the fifth item, where it says high coupon bonds show a smaller percentage change than low coupon bonds. That's where duration is going to come in. So let's begin discussing duration analysis. It's quite extensive. It has a lot of uses in bond portfolio theory and bond management. Very, very useful. It'll take us through most of this video, and it'll even be covered in part of another video on bond portfolio management and the management of interest rate risk. So what is duration analysis? Well, it boils down to this. A percentage change in a bond's price, that's what that says, is approximately equal. And I'll talk about why it's approximately equal instead of a pure equal sign there. To D, which is the duration measure, times a change in yield to maturity divided by 1 plus the yield to maturity divided by 2. So as soon as you see divided by 2, it's kind of telling you we're dealing with semi-annual bonds. And so I'm looking at this with on a semi-annual bond. And if it wasn't a semi-annual bond, it was an annual bond, you wouldn't have this little divide by 2. So probably the best thing I could do to introduce this concept of duration is to show you an example. So we're going to start off with a bond. Let's say we have a 2.5-year bond. It matures in 2.5 years. It's a semi-annual, as I just said, semi. It's a 2% coupon rate. And the yield to maturity, you can read that, is 3% per year. So what we want to do is we want to calculate the duration. We want to calculate that D term here. And I haven't really explained this formula because I'm not ready to yet, so hold on. But we're going to calculate this D, okay? And this D will help us determine the percentage change in the bond price, because we're going to know the change in the yield to maturity. We'll know what the yield to maturity is divided by 2. We just need to calculate this D for this particular bond, and then we'll know how much the bond price changes for a given change in yield to maturity. So the whole focus is on calculating this D, which is sometimes called Macaulay duration. So the way to do this is intuitively is to show you a table, to build a table. And we're going to have in the table T, which is really a year. And so T standing for time, or you can think of it as year. And so we're going to have the first semi-annual period, and then it'll be 1 year later. Okay, so this is a half year, this is 1 year, then 1.5 years, and then 2 years, and then 2.5 years as time goes on. Now, we need the cash flow for the bond. Well, that's kind of simple because you already know that. It's just 2% chopped in half because it's semi-annual times 1,000. So the face value, by the way, like we've always been using, is 1,000. So that means the cash flow is 10, 10, 10, and then 10 plus 1,000 for the maturity of the face value. Okay. Now what we need is we need a discount rate, because we're going to discount some cash flows. And the discount rate is going to be based off of this yield to maturity. And so what we want is a discount rate for the first half a year. So, think of it, 0.5, 1.0, 1.5, and so on. What is the interest rate? What is the discount rate associated for that half a year? Well, it's 1 over 1.015, 1.5%, because we chopped this in half, to the 1 power. And the discount rate is 0.9852. So you know how to interpret that. If you invest $1, if you get $1 right here, let's just assume you get $1 right here. What's it worth today? It's worth 98.5 cents. Given that there's a 3% annual rate, chopped in half, really 1.5% for this time period. Okay. Now, we also need to calculate these other discount rates associated with this cash flow right here. This cash flow is going to get this discount rate, which is 1 over 1.015 squared. That'll be 0.9707. And this will be 1 over 1.105 cubed. And this will be 0.9563. And then 0.9422. And then 0.9283. Okay, so those are our discount factors. Now what we want to do is we want to calculate the present value of the cash flow. And the present value of the cash flow is nothing but the discount factor multiplied by the cash flow. So multiply these two together. And this will be $9.85. This will be $9.71. And I'm doing a lot of rounding. There's going to be a lot of calculations. I'm going to do a lot of rounding. Hopefully, it rounds it works so that when I round up or round down, it all nets out. But we should come close. This will be 956, 942, and this is 937.58. So the sum of this comes out to be $976.12. What is that? Well, that's the value of the bond, because the value of a bond is the present value of all its cash flows. Okay, so that's pretty easy. We'll keep this in mind. Hold that that thought, so to speak. We're going to use it again. Now let's look at the present value of the cash flow divided by the price or the value of the bond. What is this cash flow as a percentage of this value of the bond? So you take 985 divided by 976. I mean, you do that, that's about 0.01. And then the 971 divided by 976, it's about 0.01. 956 divided by 976, you get the pattern here. Okay, so the way to interpret this is this cash flow represents about 1% of the entire cash flow of the bond in present value terms. This cash flow represents about 1%. This is a little less than 1%, a little less. And then this cash flow, the $937 here, that's worth 96% of all the cash flows associated with the bond. So this has to add up to 1. So that's your check. There's 2 checks here to make sure you get things right. That should be the price, and this should add up to 1. Now, what we want to do is we want to take T, we want to take this time factor and multiply it by the present value of the cash flow divided by P. In other words, take this times this times this times this, and so on. And we get 0.005, 0.01, 0.0, and 2.401. Add that up, we get 2.45 years. Duration is measured in years. It's one of the first things you should remember. It kind of makes sense because duration, sounds like it's measured in over time, and it is. So it's 2.5 years. Now we are in a situation to plug it into this formula. Minus 2.45 years. Okay, you can lead. Okay, and now we have to come up with a change in the yield to maturity. And let's just say we're going from 3% and we're going to go up to 3.75%. So that's 0.03 minus, it's 0.0375 minus 0.03. And that would be 0.0075 is the change. Okay, it's a positive change. And that's why I had to make sure I had to write this. So we're going from 3 to 3.75. That's a positive change in yield to maturity of 0.0075 decimal form, divided by 1 plus the yield to maturity, this yield to maturity where you start with, divided by 2. And we do this, we get approximately minus 1.81%. What that says is, look, if we take this bond that we just looked at here, and we increase the yield to maturity 75 basis points, then what's going to happen is this bond price will fall. Notice that negative sign. See, that negative sign means when this is positive, this change in yield to maturity is positive, it means the percentage change in the bond price will be negative. And so it is negative 1.81%. Okay, that's not very much of a change. It's a pretty big jump in interest rates, but it's a small change because this is a very short-term bond. And as you can see further, if you had a long-term bond, right, and you had like a 20-year, 30-year bond, you'd keep doing this analysis. This guy right here, this would be a much bigger number. It's never going to be greater than the maturity of the bond. So this bond had 2.5-year maturity, and it's just less. If you were to have a 20-year bond here, you'd have a duration, I'm just guessing, like maybe 17, 18, something like that. And if you had a 30-year bond, the duration might be 25 years. So the duration for a coupon bond now will always be less than the maturity. I should be clear about that. Later on, I'm going to show you that if you have 0 coupon bonds, the duration of a 0 is the same as the maturity of a bond. We'll get to that. But we're not quite ready for that yet. So now the question becomes, how do we know, let's get back to this, how do we know this is right? And this is where people, believe it or not, in my mind, this is where people get stuck. And I ask students in class, well, how do you verify this number? And they're so lost in the numbers that I gave them that they don't stop and think. Well, the price was originally 976.12. That was at a 3% yield to maturity. Now what happens to the bond if it's at 3.75 yield to maturity? Well, it's going to be n equals 5, right? There's 5 semi-annual periods for over the 2.5 years. We're going to have a y, or interest I/y, which is 375 divided by 2. That's going to be 1.875%. And we're going to have a face value of $1,000 and a payment of $10. Now when you plug that in, out will pop, when you hit compute PV, out will pop 958.61. Okay, so we increased interest rates from 3 to 3.75. We should see a drop in bond prices. We do see a drop in bond prices. Now what percentage is that? 958.61 minus 976.12. And that equals 0.01794 negative. Okay, so this will be negative. So negative 1.794%. Pretty close, but not exact. This is the exact amount. I mean, look, we ran it through the calculator. This is the exact change. Minus 1.794. We estimated, and hence this squiggly equal sign here, of 1.81%. Now it turns out the duration, this is price and this is yield to maturity. We have a curved relationship here between price and yield to maturity like I showed you before. It turns out that duration assumes a linear relationship between bond prices and yield to maturity. So when you change the yield to maturity like I did right here, we start from that point. Small changes in the yield to maturity won't have much, there won't be much error. So there's a very small error here. So we didn't change things too much, 75 basis points. So basically if I can't even distinguish that because of the thickness of my marker line here. But there is a difference. And so what happened was we went from 3 to, let's exaggerate here, 375. And let's go down. So let's say a 75 basis point jump is this big jump right here. Can you see that, right? The width of my finger. And so here we have a drop of minus 1.794%. That translates into a 958 right here. 958.61 right there. The estimate was minus 1.81, or let's see if I can write it here. We start off 976.12, 1 minus 0.0181%, this guy right here. That comes out to be 958.45. So this would be 958.45 right here. So this little difference, this little gap really says that, look, we're off about 16 cents. And the point is, duration is on this straight line. It'll always underestimate the price. The price will always be slightly higher as it was here in reality. That's the problem with this approximation. The approximation gets more sloppy as the change in interest rates gets bigger, and you have a bigger and bigger gap here and a bigger and bigger gap here, for example. Okay, now that's duration analysis. So again, what did we just do? We just estimated the percentage change in the bond price for a bond this way. We came up with the duration, and from that duration we could estimate the percentage change in bond price. This is how sensitive a bond price is to changing interest rates. You change this interest rate, how much does it change the bond price by? That's what duration is used for. It's also used for a whole bunch of other things, as we're going to learn as we continue on with this video and even the next video. So now let's cover duration characteristics. Remember we looked at bond price characteristics? Now let's look at duration characteristics. And we're doing this so we better understand what drives bond prices when interest rates change. What are the factors that make it bigger or smaller percentage change? The first characteristic is that the duration of a zero, I'll abbreviate D with a little z here, equals the bond's time to maturity. Okay, so if you have a 3-year zero, that zero's duration is 3 years. And you can see that quite easily here. Imagine you had a 2.5-year zero where all you had was a cash flow, right? One cash flow. All these cash flows were zero. So all these present values were zero, and the weights here are all zero. There's only one cash flow, matures for 1,000. So the present value of that cash flow is going to be the price of the bond. The entire weight, 1, will be on this single cash flow. And therefore, when you do this math, and I invite you to do that, just make all this zero so you can ignore all of this, make this $1,000, keep this discount rate, put this, multiply the 0.92 by 1,000, so you're going to come up with $928.30. That's going to be the value of the bond because everything here will be zero. So this will be $928.30. All of the weight will be on this one cash flow. So this will be a 1. All these will be 0. And then all these will be 0. And this will equal 2.5, which sums the 2.5 years. Okay? So therefore, zeros represent the riskiest type of bond you can have out there given a change in interest rates because they only have one cash flow. So zeros, you can see right away that zeros are pretty sensitive to changes in interest rates, all else being equal. The next thing we want to do is say, look, the next characteristic is that the duration of a portfolio equals a weighted average of the durations of the bonds in the portfolio. The bonds in the portfolio. Okay, so what's the weights now? The weights are the present value of the cash flows associated with that bond relative to the price of the bond in the portfolio. The value of the whole portfolio, I should say. So let's say it's the market value of bond 1 divided by the market value of the entire portfolio. That's what I should say. Now, we can apply that to this bond. Now remember I told you way back, I said, look, you know, a bond, you can think of a bond, a coupon bond like we just looked at, as a portfolio of zeros. So think of this cash flow as a zero that matures in a half a year. You're going to get it right here, and you're going to get $10. Then you're going to get this $10 at this point right here on the timeline. This $10 here. You're going to get this $10 at the 2 point. And then at the 2.5 year mark, you're going to get 1,010. That's another zero. So this is a portfolio of zeros. Oh, okay. So then if we treat this as a portfolio of zeros and we use this formula, then we ought to be able to come up with the 2.45 years we just calculated. So let's try it. So the market value, so I'm going to take these, to be clear, I'm going to take these numbers and I'm going to multiply it by time. This is the duration of each security, assuming every one of these guys is a zero. And this is how it looks. So that's the 0.1. This is a half a year. 1 year. 1.5 years. Times the 2.5 years finally. If you add this all up, you get 2.45 years. A little rounding, but hey, look, I'm rounding in a lot of places, so I'm not too concerned. So therefore, I just showed you that the duration of a portfolio is simply a weighted average of the durations of the securities in the portfolio. So think of a coupon bond as a portfolio of zeros, a package of zeros. Now let's move on to other duration characteristics here. Now the next characteristics, the third characteristic of bond duration is that holding maturity and yield to maturity constant. So we're holding maturity and yield to maturity constant. A bond's duration and therefore its interest rate sensitivity are higher when the coupon rate is lower. Well, you can see that right here. Again, what if you were to drop these coupons to zero? Leave the yield to maturity at 3%, leave the maturity constant. Remember, it says holding yield to maturity constant and holding maturity constant. What if you were to drop the coupon? Well, drop these to zero. And this would be at just 1,000. And what would happen? The duration would go up. Now, what happens if you would increase these cash flows? In other words, increase the coupon, say 10%. You plug in 50, 50, 50, 50, and then 1,050 here. You're going to see that it tilts the weight of the weight here. It's going to tilt the weight so that the duration is lower. So here's the way to think about duration. See if I can draw it here. What we just saw, we had $10. We had, let's see, the first 6 months, 1.5, 2, and then we had the 2.5 here, and we had the $10 plus the $1,000 cash flow. So I'm just showing you graphically. This is $10, $10, $10, $10, $10, and here's $1,000. Probably not drawn to scale, and that's done at 2.5 years. We get that last cash flow. Well, you can think of duration as a fulcrum that balances these time periods. And what's balancing the time periods? Well, the time periods need to be adjusted by the present value of the cash flows. So the present value of this cash flow is here, drops down a little bit, drops down a little bit, drops down a little bit, and it drops down a little bit for this one also. So you take the present value of these cash flows, graph them out here, and duration is basically the fulcrum that balances these cash flows. So if you have a zero, you only have one big $1,000 cash flow at year 2.5 in this case. So the fulcrum that would be needed to balance this would be at 2.5. Now, if you put more weight on these cash flows early on, like I said, let's boost the cash flows up to the coupons up to 10%, then what would happen is, or $50 coupons for every half a year. In any case, regardless, you would be increasing these bars here, and the fulcrum would end up moving to the left. So think of this as a big adult. This is a bunch of little kids. How would you balance this seesaw with this fulcrum? And that's what duration basically does. It balances things. It balances the present value of the cash flows. Okay, not the actual cash flows, the present value of those cash flows. But look, given our interest rates are so low, this is not a bad depiction of it because the present values are not too far away from these relative bars. Okay, let's cover the next characteristic. So the next duration characteristic says this: holding the coupon rate constant and the yield to maturity constant, duration increases with maturity, but at a declining rate. So here we have maturity, here we have duration, and it's important to remember what I just said. Holding the coupon rate constant, we're looking at coupon bonds. We basically have a relationship that looks like this. If you have zeros, then you have a relationship that looks like this, because the maturity will equal. So if we have a 3-year bond, then we'll have a duration of 3. If we have a 10-year bond, we'll have a duration of 10 years. But when you have a coupon bond, it starts to flatten out. And again, let's look at the graph. If we had a bond here that's long term, and then we had this big last cash flow, right? Then the duration would be somewhere here, right? So you have all this weight out here, kind of moves the fulcrum to the left so to balance this out, compared to if we had just a short bond. We had that last big cash flow. On a relative basis, we'd be more in this direction. And so what happens is these coupons soften the effect of interest rate sensitivity. That's what this is saying. You're softening the effect of interest rate sensitivity due to these coupon payments, because these are really short-term zeros which have lower durations, right? So you're putting weight on these low durations here. And if you have a zero, then you're putting no weight on this. 100% is on this particular cash flow. So the next characteristic is holding maturity and the coupon rate constant. Duration, in other words, interest rate sensitivity of a coupon bond are higher when a bond's yield to maturity is lower. Okay, let's look at it this way for a second here. It says hold the maturity constant, hold these cash flows constant. If you lower the yield to maturity, which means when you lower the yield to maturity, you actually raise this discount rate. Okay? This number goes higher, which means it's putting more weight on these end cash flows. And when you do that, you end up with a higher duration. So keeping maturity constant, coupon constant, you lower this yield to maturity, it raises this discount factor, right? So think of a yield to maturity of 0, right? So what's this discount factor then? This discount factor is 1. There's really no, it's not really discounting anything because it's just 1. That would make this number larger. The other way to look at this is, look, you're holding maturity constant, you're holding cash flow constant for the coupon, and it's basically saying this. When you have yield to maturity here and you have price, then for an equal change in interest rates, you're going to have a much bigger change when interest rates are lower, when the yield to maturity is lower, right? You're going to have a much bigger price change than when the yield to maturity is higher. That's another way to translate that characteristic. Now, the last duration characteristic is not very intuitive, and it says this. The duration of a perpetuity is equal to, and I'll write it out, the duration of a perpetuity equals 1 plus the yield to maturity divided by the yield to maturity. Now, I'm telling you that that's not very intuitive because, look, based on what I told you earlier, you can think of duration as this fulcrum that balances the present value of all these cash flows out. You have a long maturity bond. Well, this fulcrum is going to be way out to the right compared to a short duration bond. It's more likely to be to the left. But what if you have an infinite bond? It just keeps going and going and going. You'd think, well, the fulcrum has to be way out there to infinity. That's not what that's saying. What I am saying is that the duration of a perpetuity is finite. So if we had an example, let's say the yield to maturity is 3%, then we would end up with a duration of 34.33 years. Certainly not infinity. And then you need to back up and ask yourself, okay, maybe it doesn't make sense that it's infinite. And another way to look at it would be, well, if you had an infinite bond, a perpetuity out there, infinite maturity, and interest rates changed a little bit, well, the bond price would change by an infinite amount. So you can't have a duration that's infinite because a little change in yield here is going to result in an infinite change in bond prices. Have you ever noticed an infinite change in the bond price? The answer is no. So we're at the end of the video, but we're not finished talking about duration. As I said earlier, duration has a lot of aspects to it. It's the workhorse of bond analysis. And so we want to employ it further on in another video to take a look at how else we can use duration to better understand bond portfolios.